I would just briefly like to mention the project software tool called Spatial, which really should be in better shape. It was running well for a while, and then I found compilers began to give increasingly rude error messages which indicate a major overhaul is needed. Currently, it will not compile unless you use versions 3.3 of GCC or thereabouts. It is reasonably stable on a Mac running Panther OS, which has that version. It's still working well enough for me to develop ideas, and I'm going to show a video of a program run shortly. Spatial has a simulator for a 32-bit ARAM and two supported languages, Earth and Space. Earth is an assembly language which is significantly more user-friendly than machine code. It has constructs for replicating code patterns and relative jump numbers, so you don't need to recalculate register addresses when editing code. Space is a high-level language with a non-standard syntax and does not directly support persistent or live code, but could be made to do so now to some extent. A future version will offer direct support for interactive modules to model data flow, streamed computation, and motivating examples for process algebras. Space is intended to be fully general purpose with a functionality comparable to C. Now here I include a table of various low-level Earth modules with register counts and cycle times. Most are self-explanatory. The RAM implements a RAM type read at runtime and accepts as input a register index and outputs the contents. The WRAM implements a write at runtime. The 32-bit machine is not big enough for larger programs, but a 64-bit machine would occupy more than 9 petabytes. Well, if a backend for a larger machine at any rate were implemented for the low-level virtual machine, then a simple semantics would be available for the majority of imperative languages. I now show a video of a compile and run of the 8-bit look-ahead carry adder that was actually written in Space. So we are editing an existing module, carry adder 8, to show a compile run, and the code's been read, and Spatial's asking whether the read code is okay, and it's okay to update the database, and it is. We can now run the code by entering the module name. Okay, it's compiling the code, loading the machine, and asking us to enter inputs. Say 124 and 123. The machine runs, and there you can see the output 247. And I'm just going to scroll up a little bit, and your program halted normally without error. It executed 110 cycles and an average of 14.24 instructions per cycle. And that's a run of the ARAM. I have included a printout of that Spatial session on the website. Alpha RAMs with infinite memory are now described, which are Turing computable. For indefinitely large inputs, the Turing machine has an infinite number of tape squares and a cursor which can be moved leftwards or rightwards, one square at a time. A more extensive helping of the same trick is used in deriving a Turing computable version of the ARAM called the BRAM, and we assume a cursor is essentially a numeric address or part of a coordinate numerical address of a memory location. The sequential BRAM is presented informally here to save time. Memory consists of an infinite sequence of ARAM type blocks, sigma 0, sigma 1, etc. Each register in each block has a cursor, which is capable of pointing to any block. For simplicity, we consider a sequential machine here. Like a von Neumann machine, the sequential BRAM allows only one instruction of only one memory block to be marked or executed in situ per cycle. In addition to the 4 ARAM instructions with the jump modified so that it can only mark a single instruction, there are an extra 2 instructions with opcode 100 and 101, which manipulate registered block pointers, all depicted in Table 5. If it is stated that an instruction points to a memory block, it is meant that the register in which the instruction resides points to a memory block. At the beginning of each run, each register points to the same block as the register itself resides in. The sequential BRAM begins a run by activating the instruction in register 1 of memory block sigma 0. Like a von Neumann machine, it then executes the instruction in the succeeding register of the same memory block and so on, unless instructed to perform a jump or conditional instruction. A write instruction will apply to the memory block it is pointing to, similarly for a cursor move, jump, or conditional whose cursor may have been moved to point to a different block. Once again, there is an error scheme which is not shown here. Now, this is a simple program for incrementing an indefinitely large integer. The integer is stored as a succession of bits in the 00 cells of the succession of memory blocks after sigma 0. That's okay because it's only sigma 0 that has the busy bit. The 01 bit of a block will be set to indicate if the block contains the final most significant bit and reset otherwise. To avoid redundancy, it is assumed the most significant bit of the integer is set. The program occupies 26 registers, which is quite compact. The main loop begins by moving the cursors of selected instructions onto the next block, after which the computation part of the loop is executed. The only other BRAM program that has been written, as far as I know, is a simulation of a one-tape Turing machine, which appears in Appendix A of the main report. The parallelized version of the BRAM is shown here. Note the only difference is that the jump has an offset allowing plural markings. The cursor move instructions could be given an offset to encompass multiple registers, but I chose not to because its instructions are usually segmented and not contiguous amongst those that you might want to move cursors of. So that's why I chose not to include offsets. A formal definition of this machine is attached to the slides. The machine has a more complex error scheme than the sequential BRAM. Now, so far we have only considered finite markings, but this machine could support infinite markings, activating an infinite number of modules, which individually complete in finite time. I would also mention that the notion of a cursor can be extended to handle finite and infinite dimensional spaces whose points are memory blocks. There is a machine for supporting uncomputable algebras, and there's a route for ascending the transfinite hierarchy in the cardinality of markings and the set of all registers. In a brief review of related work, 3 references are cited which describe potential bit-level machine models with parallelism available. I would characterize a simple Cartesian product of Turing machines as ad hoc, like the von Neumann network, and will focus instead on multi-tape machines. Turing's work was of course seminal, and his notion of a tape cursor was essential for the BRAM. The Turing machine can be bit level, but a parallelization of n instances of a one-tape Turing machine with m states results in an n-tape Turing machine with m to the n states. I couldn't find a reference for this other than a section in my main report. Consequently, the parallelization of, say, 256 machines with 2 or more states will result in an instruction table with more tuples than there are particles in the universe. Consequently, multi-tape TMs cannot be said to be tractably simulable with respect to parallelism. Alpha RAMs use Petrie's great idea of a marking. Petrie nets normally model distributed systems, but they could be repurposed for modeling asynchronous and synchronous digital circuits, of which more in the next reference. However, the implementation of an n-input logic gate in one transition requires 2 to the n places. Similarly, in Winskill's event structures, they require 2 to the n events to model an n-input logic gate in one causation. Finally, the high-level synthesis paradigm should be mentioned, which I consider work more closely related to alpha RAMs. Inner loops in C programs are interpreted as register transfer language descriptions in order to accelerate critical parts of code by implementing them as digital circuits. Logic simulation tools can give simple machine-like semantics to RTL descriptions, but RTL descriptions of large program interpretations are enormous, and in addition, circuits may deal with bits, but they are not fundamentally primitive on the bit level. Selection in a C program is not implemented as a fundamental feature, but is a high-level construct involving multiplexers and demultiplexers. Circuits are deep and complex DAG structures with memory locations attached and impose a conceptual bias commensurate with their level of abstraction. Before concluding, I'd like to propose a parallel invariance thesis in addition to Boas's theses, which might provide a means of comparing models. So the thesis is reasonable parallel machines can simulate each other with constant factor overheads in space and time. Now, this is not a rigorous statement because we need to find a way of quantifying space and time measures across models. I provisionally make the claim that if the standard parallel model were the synchronic BRAM, then Turing machines and unmodified Petri nets and event structures for digital circuits would not be reasonable parallel machines. And finally, we have a slide with some conclusions. Alpha RAMs present ultra-fine grained machine models with a simple semantics based on just 4 simple instructions. They are a neutral machine platform for language design with tractable simulations of what-if scenarios and a basis for investigating processes running on a basic device rather than in a formalism abstracted from hardware. A member called the synchronic ARAM is put forward as a finite machine model for general-purpose parallelism and concurrency. For hardware design, physical constraints can be introduced in a least restrictive order, thereby reducing bias towards existing architectural types. BRAMs have infinite memories and are Turing computable. And finally, alpha RAMs provide machine concepts underlying synchronic computation. Thanks for listening, and if you're interested, please download further slides and papers from isynchronize.com.